So after the air control, I'll just want you to recap what we discussed in the morning.
Yes, sir.
The analogy of aircraft taking off and
Okay.
how the wind turbine rotor is designed.
Yes, sir.
So just take a cross section of the blade here, okay, which is
Okay.
shown here, a cross section of the blade, okay.
Okay, sir.
The wind flow is the blue line around the
Yes,
blade,
sir.
around
Okay.
around the blade, okay. So the rotation will happen like this. So the lift force should be perpendicular to the wind flow, like
Mm.
this, okay.
Okay.
If you optimize that lift force, that force into this lever arm, the radius, will be the torque, the rotation, okay. It will try to rotate the rotor.
Yeah.
This we are achieving by aerodynamic shape and pitch control of the blade, okay, like this.
Mm.
And in addition, we will have some additional uh, edge effects, okay, to efficiently capture the wind energy. And this is from thin air, which is from 3 meter per second wind. 3 meter is approximately 12 kilometer per hour, okay, and up to 25 meter per second only we can extract. Beyond that we cannot extract, okay, in the case of a wind turbine. The same thing, if the aircraft has to lift, the lift must be generated by burning fuel to gain about 250 kilometer per second wind speed, which is an order high, okay,
Mm.
when compared to the maximum wind speed at which it can produce energy. So that's why this produces energy from transient ambient simple wind, okay.
Mm.
Whereas here we are deriving the lift force by burning gasoline fuel to gain a very great wind speed, great speed of the aircraft. Relative
Mm.
speed of the aircraft only generates the flow in the aircraft wingspan.
Mm.
So with that only we are able to lift the payload in aircraft. Similar way, maximum lift will give good generation in the rotor.
Mm.
Okay, that's the concept. Okay,
Okay.
right. Then to compare, if you want the tons of weights, blade may weigh around 11 tons, rotor may weigh around 60 tons, nozzle weight may be 82 tons, a 80-meter tall tower may weigh around 62 tons. Overall, if you see 200, 300 tons weight will be the wind turbine weight. It's as good as 48 elephants weight. Okay, and it is as tall as the Boeing 747. Today's wind turbines. Okay, in
Mm.
fact, much taller wind turbines are there now.
Mm.
Even in India, we got 5 megawatt by Adani.
Yeah.
Yeah, right. Uh, Suppose you don't have any uh, software with you. Okay, you have been told to find out what is the energy that will be generated from a particular wind turbine at a particular site. Okay, then this Betz constant limit and all that. The power is half rho A V cube, okay, into CP,
Mm.
the power coefficient, which depends on the uh, tip speed ratio versus CP curve. You remember that
Yes, sir.
tip speed ratio of the CP curve. Okay, and once you know that, uh, if you have this power curve for the nameplate curve, power curve is nothing but wind speed versus how much power it will generate in that wind speed, that wind turbine. Okay, it is human design. We design that by aerofoil design, pitch control design, and controller design, power electronic design, everything. So at what wind speed, how much power will be generated? Are you able to see that clearly?
Yes, sir.
Yeah. This is called power curve of the wind turbine. Okay. And at the site, you would have got 1 year data, wherein you would have measured values and the frequency distribution. The bell curve will be available. What percentage of hours this particular wind speed was there. Okay, you have to
Mm.
match the site along with the power curve, and then you can find out what is the uh, average output, because the wind turbine may be operating at 3 to 4 meter, up to 3 meter per second. It may not operate at all. Okay, normally
Mm.
that's why I showed you the previous slide. Yeah, the previous slide. You remember the range is 3 meter per second, up to 3 meter per second. Most of the wind
Yeah.
turbines today, even the large wind turbines, may not operate at all. Okay,
Okay.
that is called cut-in wind speed. Okay,
Cutting industry. Okay.
cut in,
Mm.
cut in.
Cutting,
When
na?
cut in
Ah.
means when the wind turbine rotor starts rotating, that is cut in. Starting wind speed, minimum starting wind speed, 3 meter per second. Okay, is that point clear?
Yes, sir.
Okay. Similarly, beyond 25 meter per second, that is 100 kilometer per hour, if there is a cyclone, the wind turbine will be stopped automatically, because it will generate more drag, which is in the direction of the lift, direction of the wind flow. Okay, drag will be in the direction of the wind flow. It will try to
Mm.
press the rotor not to rotate. It will be air brake, like it's like a air brake applied
Air
on the
brake.
rotor. Ah, okay. So when such a thing happens, what we do is we start applying the brakes applicable for the rotor. It may be a disc brake like in what we have in our car. Okay, disc brake, which will stop the rotation,
Mm.
and then resist the cyclonic wind speed, which is 100 kilometer and beyond, kilometer hour per hour,
Mm.
25 meter per second.
Mm.
This is called cutout wind speed.
Cut out.
Yeah, cutout means beyond which the wind turbine cannot efficiently produce power from the wind. So you stop the wind turbine and make it resist and live longer to generate more. Okay.
What is the measures usually for cutting speed is 3 meter per second.
Yeah, cutout is 25 meter per second.
Okay. So whichever when the wind is goes more 25 meter per second, then it will not rotate, sir.
Yeah, it will stop, because it will slowly come into the the pitching of the blade will come into smooth flow. It will allow the wind to pass through. Okay,
Okay.
it will not generate the lift. It will pitch
Okay.
out. It will pitch out in such a way that
Mm.
it becomes a smooth airfoil.
And okay.
That is
Okay,
this.
understood, sir.
Then the wind will simply pass through. Lift will not
Mm.
be generated. So it is just like, we take out when you want to apply brake in your car, you remove the accelerator first,
Ah.
and plus press the clutch. So the power is not transferred to the rotating shaft. Now you apply the brake, it will work faster.
Okay, sir.
Okay, similar to that. Okay, you first you go out of wind by so, changing the pitch angle in such a way that it becomes a smooth aerofoil
Okay.
to allow the wind to pass through without generating any lift. Okay, and whatever is the extra thrust load that is coming on the tower and the blade, it will resist by standing still.
Okay.
Okay, that is called
Okay.
cutout wind speed. And in between there is one which is called design or rated wind speed. Okay,
Mm. Mm.
so that is what is shown in this picture. So a wind turbine is designed in such a way, it cuts in at 3 meter per second. That means this beyond this wind speed in this site, it will start producing power. Okay, but it will produce power only 200 kilowatt as against 1500 kilowatt. Is it clear?
No, sir.
Not. Okay. When the wind is only 3 to 4 meter per second,
Mm.
as per the designed power curve of the wind turbine, the 3 meter per second, it will only generate up to this point. This is power,
Yeah,
generated
understood.
power, and
Okay.
this is wind speed at a hub height.
Yeah.
So at 3 meter per second or 4 meter per second, it will only generate say 150 or 200 kilowatt power
Okay.
as against 1.5 megawatt.
Oh, okay.
So this is called the power curve. This particular point where it generates maximum power, which is the nameplate capacity of the wind turbine, is called rated wind speed.
Ah.
That is design wind speed.
Mm.
Okay, it is not called design wind speed, it is rated wind speed.
Mm.
So at this point only, it will generate maximum power. That is, in this particular turbine, at 12 meter per second only, it will generate maximum power.
Maximum power.
Okay, right. At 7 or 8 meter per second, or 6 or 7 meter per second, somewhere here, it will generate about 1 megawatt instead of 1.5 megawatt.
Mm.
Okay,
Okay.
at 10 or 12 meter per second, it will generate this much megawatt. But the wind available in this range is limited, whereas the wind available in this range is higher.
Yes, sir.
So, at whenever the wind turbine is operating in this slope, it will not be producing full power
Mm.
of the nameplate capacity. Is this clear?
Mm. Yes, sir.
So, the peak output, even though the wind turbine may be working 5 months during the season, okay, the peak output will be only during when the wind speed is at rated wind speed and beyond. Okay,
Okay.
up to 25 meter per second.
Mm.
So that is why the average output, actual generation divided by the peak output, which is called the capacity factor, which was earlier approximately 30%. Now it is around 40% now with modern wind turbines because of
So
efficient pitch controls.
can we straight away calculate that whatever megawatt by 30%, like into 30% will be the utilization factor in that way also?
Not that way, because at each wind speed, uh, how many hours that wind speed is there in that year, depending on that, that much kilowatt hour will be generated.
Okay.
So you have to sum total of the multiplier. You have to multiply the velocity cube or the power into the probability of that power, and now how many hours it happens. You have to add.
And
Okay, you have to
okay.
sigma. That should be a sigma.
Sigma.
You have to, for each wind speed bin. This is what I told you. Wind speed bin,
Mm.
1 to 2 meter per second, 2 to 3 meter, 2 meter per second to 3 meter per second. Each wind speed bin, how many hours the wind turbine was working in that particular year,
Mm.
in that particular site, will be reflected in the power generated.
Okay.
So,
Okay.
the numerator is actual generation for the entire year. Okay, the denominator is assuming that the wind turbine would have worked 8,760 hours at the rated capacity, then what would have been the output? That is the denominator.
Okay.
So this is called capacity utilization factor or capacity factor.
This
Okay.
that means this capacity utilization factor vary from project to project.
Yeah, very much, very much. Because it is not only site dependent, it is also mission dependent. And in addition, there are other things like grid availability. Then you may be asked to back down. Okay,
Who will give this, this average output and
which average
week,
output?
the average week output, no?
This wind
Like we
speed.
have to calculate only from the data, everything.
Yeah, from your SCADA data.
Hmm.
I'm not saying average output. You can put actual generation.
No, no. For initially, while for the viability of the project, we will doing this, no, sir?
No, viability of the project itself, you can compute completely using the probability of the wind speed occurrence. You can compute assuming the efficiencies of your machine and the grid availability, everything.
Okay.
Okay, you can compute the actual generation itself.
Okay, sir.
Okay, maybe 1 minute. Let me check whether I have that one calculation we did for Kerala. So yeah, this is yeah. So there is one uh, Ayurvedic hospital factory, okay, in Kerala. Uh, they wanted to make a viability study. So we made uh, about 8 models of wind turbines. We took the power curve, okay. To make anonymity, we have normalized the power curve. That means 0 to 1 only we have shown. What is the
Hmm.
capacity of the model machine? We have not said because we have to be anonymous. We cannot take somebody else's power curve, okay. And then we did this calculation and how we can um, suggest how much energy will come from that. We can calculate using Excel sheet. Okay, we can calculate and find out and how much energy each machine will give. Depending on if you change the machine, the energy generated will vary. Maybe we'll go into details little later. Okay,
Okay.
uh, you can use a Excel sheet or there are. It's not so difficult. 1 minute. It's, it is not so difficult. So you have to have the number of hours of operation of the wind turbine. Okay, you should have the number of hours of operation from the probability of wind speed distribution at the site. Okay, assuming that the
No.
grid was available 100%. Okay, if there is a grid outage or a back down, um, then you have to take that back down into account and calculate how much time the wind turbine was operating in what wind speed. Then take this power curve value, multiply with the probability of number of hours into that. Then it will come as 200 kilowatt hour at this wind speed bin plus uh, 4 to 5 wind speed bin about 400 kilowatt hour at 6 to 7 it's about 5000 kilowatt hour because and beyond that like this you pick up the power from this and number of hours of operation in that power. Okay. Ultimately energy is power into time, right?
Yes, sir.
Kilowatt hour. So you have to convert this power curve along with the probability of occurrence of that particular wind speed bin, okay, in that particular site, or if you have measured the wind speed itself in that
Hmm.
particular year simultaneously using your anemometer and stored in the SCADA, you can use that directly. Okay, the probability of that this thing, number of hours of operation in 3 to 4 meter bin. That is 150 kilowatt into 400 hours plus uh, about 4 to 5 meter per second, 5 meter per second into um, 400 kilowatt into 600 hours, like that. It will keep on increasing up to 6 to 7 meter per second. 6 to 7 meter per second will be around 1000 kilowatt into
1,000
say
kilowatts.
3000 hours.
Mm.
Okay, like that.
Mm.
And it will be maximum at 6 to 7, and beyond that number of hours will reduce, but the power capacity will increase. 10 to
Mm.
11, the power capacity will keep on increasing.
Mm.
11 to 12, it will be 1500 maximum, and number of hours will keep reducing. So you will be able to get exactly the kilowatt hours in this. No, you need not give you average.
Okay.
Okay, uh, the actual generation will be given divided by the total number of hours into the peak capacity, 8760 for the entire 365 days, no,
Mm. Yeah.
into 1500, assuming that will be the capacity utilization factor. You got it now?
Yes, I got it, sir.
Okay, that is that numerator is the sigma of all the wind speed which occurred,
Mm.
and denominator is assuming that um, whatever wind speed was there, the peak output 1500 has happened fully. That is
Yeah.
capacity factor.
Yep. Sir.
Okay,
Mm.
so this is one of the parameters which is used for design selection of the site also. Okay, I'll just quickly run through another program called Bladed. Have you heard of the program called Bladed?
No, sir.
Bladed, using Bladed, you can design the entire wind turbine system. Okay, in a preliminary condition, you can design the blade. You can design the aerofoil section. Select the aerofoil section. You can design the rotor, configure the rotor, tower, and then powertrain like gearbox. Then you can design the total nacelle and controls like pitch control, yaw control, everything. Then you can do a dynamic analysis and you can simulate different winds. In the case of offshore, you can generate waves also, and you can calculate by giving all these inputs. You will be able to get blade profile design, and you can design wind turbine, how much tilt it should be there vertically so that it generates maximum power. All these things can be input, and you can completely design the blade profile onwards. You can design the generation. Okay, you can calculate the generation also. Okay,
Okay,
completely you
sir.
can design. You can do the all calculations using bladed software, which is easy to use software, and this is priced version. There is also a US version, National Renewable Energy Laboratory in USA. They have a software which is free. Actually, you can download and use it. Okay. Anyway, you don't have to go into the so much of details. Don't worry,
Yes, sir.
huh? Because
Yes,
you are
sir.
in a management level.
Yes, sir.
You should know that anyway, India is not designing seriously. Let me be frank with you. Okay, most of the designs we are importing from abroad. We don't do any design.
Oh, oh.
Yeah, yeah. Whatever they call as design office, Switzerland has got indigenization, design office, and all that. Their design offices in Germany.
Oh.
Okay, in
Okay.
India there is no design office. We only import the design, but because of the government regulation, you know the RLMM list. Have you heard of RLMM list?
No, sir.
No?
No, sir. R?
No. RLMM, revised list of models of manufacturers.
No, sir.
Okay. Uh, those are the, I will show you that in a minute. Okay. I'll just quickly go through MNRE website. I'll show you.